Hello friends, welcome to my channel. So in this video, I'm going to share two methods to locate a number of connected components in a graph or a problem that can be transformed to a graph problem. So here the example problem is Leetcode 200, number of islands. So this problem asks us to return the number of islands. So an island is the consecutive ones four directionally connected. So for example, in example 1, so this is the one island. In example 2, there are 3. For example, this is 1, and this one itself is 1, and these two ones form 1. So the constraints on this problem are that the number of rows and columns are bounded between 1 and 300, and the grid element is a string, so either 0 or 1. So with that said, let's look at the method. So the two methods we're going to share, one is the disjoint set abstract data structure, also known as union find or disjoint set first. And another method is the traversal method. So here I'm going to use depth first search. So the problem here requires to find the number of islands. So in the union find language is to find the number of clusters or the number of forests. So in the graph language is to find the number of connected components. So our plan here is to implement both methods to demonstrate the use of them. So with that said, let's first look at method 1, that is union find. So for demonstration purpose, we're going to give a disjoint set implementation as a class. So here I'm going to implement the find method with path compression and union method with union by rec. Though for this small problem itself, it might not be necessary, but it's good for general purpose use. So first, let's look at the DSU. I'm going to implement as a class DSU. So first, let's make some initializations. So self. So I'm going to use the root attributes to record the node and the parent relationships, and I'm going to use the recs attribute to store the node and rec information. The rec actually will be the cluster size. So in the problem here, or similar problems, but in general the rec can be something else. So with that said, let's look at the find method. So for this method, as we specified, and also to tailor to this problem, it will accept a position. So the position here is a tuple, like row and column. So in general, this position can be an abstract object. So first, I'm going to treat one case that is position not in the data structure yet. So that is not in the roots. Then I'm going to set the roots of the position equals itself, and the corresponding recs equals 1, corresponding to a single node cluster. Then we're going to return this position. Otherwise, so then we are going to do a path compression. So the way we do it is in this video is like this. So we're going to introduce a temporary variable called result, currently has a state position. We're going to return the final state of the result. And also I'm going to initialize a set called path, so which stores the intermediate nodes. And finally, we want to do a redirection of node root relation. So now it's a while loop where result does not equal to self roots result. Then what we're going to do is that we first add this intermediate node to the path, and then we reset the result state to be self roots of result. When we exit this while loop, then we have a state that is result equals its root. Then basically we want to return a result, right? Before that, let's do a path compression. So this actually, in some cases, can accelerate the check of number of clusters in the final stage. So for this, basically a for loop for node in path. Then we're going to set the roots of these nodes to be result. So that's it. So that's an implementation of Find with path compression. Now let's do the union operation. So self, it will accept two additional arguments called position 1 and position 2. We can understand the position 1 and position 2 as abstract objects, or we can understand them are coordinates in this problem. First, there we're going to track their delegate in the data structure. So in other words, we want to find their roots. Position 1, self, find position 2. If R1 equals R2, so nothing should be done. And if R1 does not equal to R2, meaning that position 1 and position 2 are not in the same cluster, then we're going to join them by resetting the node root relationship. So for this, we want to do it with the aid of rank. So in the vanilla implementation, we can just set the root of R1 equals R2 or in the reverse direction. That's it. But we want to add some flavor. So that is, we want to use the rank. So self ranks R1 is greater or equal than self ranks R2. If this is the case, we're going to merge the smaller cluster to the large one. So in other words, it's corresponding to set roots of R2 to be R1. And then we're going to increment the size of a cluster represented by R1 by this, by increment that of cluster R2. So that's it. So in the other case, so we're going to do essentially the same thing, but in a reverse order or direction. So we're going to set the root of R1 equals R2, and then we're going to increment the size of R2 cluster by that of R1 cluster. So that's it for this union operation. So typically, if for convenience, we can implement some methods like get clusters or get forests. So let's stop here for this. So we are going to use it inside this solution. See. So with that said, I guess we are ready to write a solution. So first, I'm going to make a remark. So this is a disjoint set union solution. So here first, I'm going to initialize a data structure. So DSU is DSU. Next, I'm going to track the information from the grid, like the number of rows, number of columns, for the convenience of iteration. So length grid 0. So next is our main work. So we want to traverse the grid and locate those positions with 1, and then we check if that position is already in the data structure. If not, we try to put that position in the data structure. Otherwise, we are going to do union. So for I in range M, for G in range M. So if grid IG equals 1, so notice that this is a string. So this is a very important, not an integer one. Then first, if not in 1, so I'm going to first make a dummy thing, so that DSU find this IG. And then we're going to check the neighbors. So for the 4 neighbors, let's see, x, y in I minus 1, y, I plus 1, y, and I, y minus 1, not y, I, j, I plus 1, j, I, minus 1 and ij plus 1. Right. So if any of the neighbors of this ij is inside the data structure, so it means that that position is also 1. So we just need to do a union, right? DSU union. So we are going to union ij and this xy. So notice that we do not need to check if the xy coordinates is inbound or not. If it were in this if for xy, so if it were in the DSU, so it should be inbound, right? So let's check this logic again. So we find ij, and then for alright, so yeah, if we like, maybe we can do a check. So here for xy in this thing, if xy in DSU, so here actually we need to do one more thing. So if xy is let's see, in DSU roots, then we're going to do the union. So if with this condition, so we do not need to check if xy is inbound, as long as xy is in the data structure, so it's inbound. So with that said, I guess that's about it. So now what we want to return is the number of clusters. In other words, so we want to find how many delegates or representatives for this data structure or the forests. So this is actually very routine. So just the length of set of the different delegates. So basically DSU find root. So for root in DSU roots, so values, right? And that's it for this solution. So let's do a special case check. Yeah, it passes a special example. Now let's look at generic case. Yeah, it passes the generic case. I guess for this disjoint set solution, so that's it. So once we have this data structure ready, so the solution actually is very short. So here let's mention that. So we implement find and union with some extra features like path compression and union by rack. So if we do not use compression and union by rack, so this basically one line code. So just or this is just very short. So that's about it for the first solution we're going to provide. That is the unified solution. Let's call it solution V1. So next, let's look at another solution. So we're going to use depth first search. So in other words, we are going to share a traversal solution. So here I'm going to use depth first search. So for this, first I'm going to track the information for the number of rows and the number of columns. M equals length of grid and length of grid 0. So that's actually the routine. And the second step, what we want to do is that we write a DFS hyperfunction. So for that, actually, we're going to write in an iterative fashion. So yeah, actually we can write it in a recursive fashion, but the iterative fashion, personally I feel, reveals more information. So define and DFS. So it accepts a position or coordinates. And then I'm going to initialize a set called visited to help us do the while loop to come. And then we are going to initialize a stack. So notice that for depth first search, the corresponding container is stack. If we would like to do breadth-first search, so here we should use a queue. So then we are going to iterate while s. Then we are going to have the position, so s pop. So here I'm using the tail of the list as the head of the stack. So once we get this, then we are going to add this position to visited. And then we're going to check the 4 directions for x, y, in, so I-1, j. So also not I-1, so R-1, c. R plus 1, c, and R, c-1, and R, c plus 1. And then what we want to do is that we check if the position is in range. So if 0 less or equal than x less than m, and 0 less or equal than y less than m. And we want to make sure this position at xy corresponds to a land that is 1. And also we want to make sure xy not in visited. So if this is the case, we're going to put this position in the stack. So that's it. So here we check the not visited at here, or actually we can check here before we add the position to the visited set. We add a if condition. If RC is not in visited, then we add this RC, so that we do not need to check here again. So anyway, so that's the while loop. Then we're going to return the visited. So the visited is actually the number of the corresponding coordinates representation of the connected components. So with that said, we finished the hyperfunction. Now let's look at the problem logic. So basically it's a call of the hyperfunction and count. So for this, I'm going to initialize a variable called count, so with starting value 0. Then we are going to make a set so that we do not repeat our previous steps. And then we're going to iterate. So for I in range m, for j in range n. Then we're going to check if grade ij equals 1, that is a land, and ij not in visited. Then we're going to increment the count by 1 because we meet another new land corresponding to a cluster if we do depth-first search. And then we're going to enlarge the visited site by union, so the corresponding traversal result, that is ij, dfsij. So with that said, we finished the main logic, and we are going to return the final state of the count. So that's it. So that's in big we put into 3 steps: information, meta information, and the hyperfunction and the count. So let's do a special case check. Yeah, it passes a special case. Now let's look at the generic case. Yeah, that's it. It passes the generic case. I guess that's about the end of the video. So here we give 2 methods to locate number of connected components or locate the components themselves. So the 2 methods are disjoint set data structure and traversal solution. So here the traversal we use is depth-first search. So if you find this video useful, you're welcome to share with your friends and watch this channel for other videos and for comments and suggestions. With that said, that's it about this video. Thank you very much.